On the tranquil morning of January 16, 1943, a profound stillness enveloped the docks of Portland, Oregon, where the SS Schenectady lay moored. This vessel, a freshly minted Liberty ship, was a mere 10 weeks old, having just emerged from the bustling Kaiser shipyards. No hostile forces menaced her existence, nor did any tempestuous gales lash against her robust hull. Yet, without a preceding tremor or a discernible warning, a sharp, resounding crack rent the air across the entire harbor. In a matter of fleeting moments, the colossal ship cleaved entirely in two, its hull brutally sundered from deck to keel, as if meticulously sliced by an unseen, formidable blade. A wave of panic rippled through the crew as the bow and stern sections sagged precipitously in opposing directions, the ship's structural integrity irrevocably compromised while tethered in the presumed safety of the pier. The tragic fate of the Schenectady was, regrettably, not an isolated incident. Throughout that same unforgiving winter, the SS John P. Gaines similarly disintegrated amidst placid waters. The SS Manhattan, a T-2 tanker fabricated using identical construction methodologies, suffered such severe structural fissures that its terrified crew precipitously abandoned ship. Between the years 1943 and 1944, a staggering total of more than 2,500 Liberty ships documented grave structural infirmities, encompassing debilitating hull cracks, extensive deck fractures, and utterly catastrophic splits. A minimum of 19 of these vessels fractured completely in half, while 3 others simply vanished without a trace at sea, disintegrating with such alarming rapidity that they were unable to transmit even the most rudimentary distress signals. These were not casualties of wartime engagement. Rather, they were ships succumbing to an inexplicable, self-inflicted demise. The United States had staked its entire strategic future on the ambitious Liberty ship program. Following the devastating assault on Pearl Harbor, which plunged America irrevocably into a global conflict, the nation faced an exigent demand for thousands of cargo vessels, needed with unprecedented speed. Conventional shipbuilding practices typically consumed 8 months per vessel, a timeline the beleaguered Maritime Commission could ill afford. It was then that Henry Kaiser, an astute industrialist with no prior experience in naval construction, put forth an audacious proposition: mass-produced freighters, conceived and assembled akin to automobiles, capable of rolling off production lines in mere weeks, not months. His pioneering Richmond, California shipyards introduced revolutionary techniques, embracing welding over traditional riveting, utilizing prefabricated sections in lieu of piece-by-piece construction, and adopting assembly line logistical principles directly inspired by Detroit's automotive factories. By the close of 1942, Kaiser's innovative shipyards were achieving the remarkable feat of launching Liberty ships in an astonishing average of just 42 days. The nation's formidable propaganda apparatus enthusiastically heralded this industrial marvel. Newsreels depicted images of Rosie the Riveter, though by then many were skilled welders, meticulously transforming vast steel plates into formidable seagoing vessels at what seemed an impossible pace. The SS Robert E. Peary established an unparalleled record in November 1942, completing construction in an astounding 4 days and 15 hours from the moment its keel was laid to its triumphant launch. Americans celebrated this prodigious output with fervent cheers. The Allied shipping tonnage, which had been grievously depleted by relentless U-boat wolf packs, was finally receiving a desperately needed influx of reinforcements pouring into the treacherous Atlantic. However, a sinister pattern began to emerge. The ships commenced fracturing, not as a result of torpedo damage or the fury of tumultuous seas, but spontaneously and catastrophically, under conditions that should have presented no challenge whatsoever. Naval architects found themselves utterly perplexed. The welds, upon inspection, appeared robust and faultless. The steel consistently met all specified metallurgical standards. Even the foundational designs were derived from proven British blueprints. Yet, despite these assurances, Liberty ships were fracturing with the fragility of delicate porcelain teacups. The fissures typically originated at points of acute angularity, such as the sharp corners of hatch openings, gun mounts, or the squared-off design elements of the hull. Once a crack initiated, it would propagate through the welded hull plates with terrifying velocity, occasionally traversing the entire length of a vessel in a matter of mere seconds. In response to this escalating crisis, the Maritime Commission promptly convened a series of emergency investigations. Metallurgists meticulously examined failed sections of steel under powerful microscopes. Engineers painstakingly reviewed complex stress calculations. Naval inspectors painstakingly crawled through the cavernous hulls, armed with precision measuring instruments. Every conceivable culprit was scrutinized: substandard steel, defective welds, inherent design flaws, or inadequate quality control measures. Yet, even as these committees deliberated, ships continued to fracture, instilling a profound dread among sailors who navigated these colossal vessels, knowing that the very hull beneath their feet might inexplicably unzip without warning in the frigid, unforgiving waters of the North Atlantic. The acclaimed miracle of mass production had, chillingly, transmuted into a maritime nightmare, and no one could adequately explain why ships constructed with unparalleled speed were failing in equally unprecedented numbers. The pivotal answer, remarkably, emanated from the most improbable of sources: a dedicated welder toiling on the assembly line, a position not typically expected to challenge established engineering directives. Bessie Hamill worked the demanding graveyard shift at Kaiser's Richmond Yard No. 3, one of thousands of resilient women who had surged into shipyard employment as men departed for overseas military service. She had been diligently welding hull sections for 8 months, a tenure sufficiently long to discern a critical flaw that had evidently eluded the highly credentialed engineers. Each night, she observed her team executing the welding of massive steel plates in a sequence that, to her practical eye, defied all mechanical logic. Hamill consistently witnessed welders commencing their work at the periphery of plates and progressing inward, or initiating a long seam at one extremity and extending it continuously to the other. As each successive weld cooled, the metal inevitably contracted, exerting powerful pulling forces that warped and distorted the plates. She could distinctly perceive the accumulation of stress, watching the very steel contort beneath the intense heat of her torch. When welders completed one section and proceeded to the next, they were, in essence, irrevocably locking that cumulative stress into the structural framework. It was, she intuitively understood, analogous to tightening the central bolts on a car wheel before adequately securing the outer ones, a procedural error destined to result in structural imbalance and eventual failure. Her immediate foreman, however, summarily dismissed her concerns. She was, after all, merely a welder, not an accredited engineer. The prescribed welding sequence, he asserted, originated from the esteemed engineering department, from men possessing advanced college degrees and specialized naval architecture training. Undeterred, Hamill persisted. In November 1943, she boldly requested a meeting with yard supervisors, an act that brazenly contravened established chain of command protocols, and could have easily resulted in her termination. She presented compelling evidence: meticulously prepared test plates she had personally welded during her own time, employing various sequences. Some of these samples exhibited significant warping and clearly discernible stress patterns. Others, however, welded from the center outward in a carefully planned, balanced sequence, lay perfectly flat and true, displaying minimal distortion. The supervisors, initially skeptical, found themselves increasingly intrigued by Hamel's empirical demonstrations. One supervisor ultimately consented to observe the production line directly during Hamel's shift. What he witnessed unequivocally corroborated her observations. Welders were, effectively, torturing the steel, compelling it to endure immense internal stresses that it would carry for the entirety of its operational life. Each cooling weld generated residual tensile tension within the metal. The prevailing construction sequence ensured that these internal stresses accumulated and dangerously concentrated at specific, vulnerable points, particularly at the sharp corners of hatch openings and other designated stress concentration zones. Consequently, when these ships encountered the frigid waters of the North Atlantic, the steel's inherent properties transformed, rendering it dangerously brittle. The combination of locked and residual stress, and this newfound brittleness created the perfect, perilous conditions for catastrophic fracture. Hamel's profound insight was elegantly straightforward. Welders should proceed from the center of sections outward, thereby enabling stress to dissipate harmlessly toward the edges rather than dangerously concentrating in the core. Furthermore, she advocated for alternating welding locations to prevent an excessive buildup of heat in any single area. Crucially, welds should never be executed in long, uninterrupted runs. Instead, a meticulously balanced sequence was imperative, one that meticulously distributed cooling stresses uniformly across the structure. These were not groundbreaking metallurgical theories. Rather, they represented practical, astute observations gleaned from someone who intimately worked with the material on a daily basis, a person who could feel the metal's subtle movements under her torch and instinctively recognize the far-reaching consequences of improper technique. By December 1943, her groundbreaking observations had ascended through the ranks, ultimately reaching Henry Kaiser himself. He was confronted with a brutal and unenviable choice. The Liberty ship program was already under intense congressional scrutiny due to the rampant cracking epidemic. To concede that the construction sequence, rather than the quality of the steel or the integrity of the welds, represented the fundamental flaw meant acknowledging that every ship constructed thus far harbored systematic defects intrinsically baked into its hull. It necessitated a temporary deceleration of production to retrain thousands of welders. It also demanded a comprehensive redesign of the entire assembly process. Yet, making these difficult concessions also presented the potential solution to the pervasive fracture crisis that gravely threatened to undermine America's entire maritime logistics chain, a linchpin of the Allied war effort. Kaiser, commendably, exhibited no hesitation. He swiftly authorized immediate and comprehensive testing of Hamel's theories, even going so far as to pull an entire hull section directly from the ongoing production line for experimental reconstruction. The very metallurgists and engineers who had dedicated months to meticulously analyzing failed ships now found themselves receiving instruction from a night shift welder who had never once stepped foot inside a college classroom. The subsequent test results proved to be both damning in their indictment of past practices and profoundly revelatory in their implications for the future. When Kaiser's team of metallurgists meticulously examined hull sections constructed using conventional sequences versus those fabricated according to Hamel's innovative methods, the disparity was both measurable and dramatically apparent. Residual stress gauges indicated that traditionally welded sections harbored internal tensions exceeding 30,000 pounds per square inch, dangerously concentrated at critical structural junctures. In stark contrast, Hamel's meticulously sequenced sections effectively distributed those stresses across significantly broader areas, with peak readings barely registering 12,000 psi. The steel itself was unequivocally identical in both sets of samples. The welds were chemically indistinguishable. Only the precise order of operations had been altered, yet the structural integrity had demonstrably improved by factors that the engineers initially found difficult to reconcile with their established understanding. The underlying physics responsible for these catastrophic failures finally achieved crystalline clarity. Steel is not a static, inert material. Rather, it possesses a dynamic crystalline structure that responds profoundly to fluctuations in temperature. When welders traverse a torch along a seam, they induce a localized temperature exceeding 2,500 degrees Fahrenheit. The metal within this heat-affected zone expands dramatically. As the weld subsequently cools, it contracts, but this contraction is powerfully constrained by the surrounding, cooler steel. The inevitable consequence is residual tensile stress, permanently locked into the structure. Unless the welding sequence is specifically designed to facilitate the redistribution and dissipation of this internal tension. Liberty ships were, in essence, succumbing to a phenomenon metallurgists precisely define as brittle fracture propagation. The specific carbon steel employed in their hulls, while designated as shipbuilding grade, performed adequately in warmer waters. However, it underwent a critical and perilous transformation when exposed to the near-freezing temperatures of the North Atlantic. Below approximately 40 degrees Fahrenheit, the steel's inherent ductility, its capacity to deform slightly and absorb stress, collapsed precipitously. Normally, metal accommodates stress by undergoing minor deformation, bending rather than fracturing outright. Cold steel, tragically, loses this crucial flexibility. It becomes dangerously brittle, exhibiting characteristics more akin to fragile glass than the robust, pliant material welders confidently manipulated in California's temperate shipyards. In California's mild shipyards, a perilous dynamic unfolded. When an unyielding, inflexible metal encounters concentrated internal strain at an acute angle, such as the sharp, rectilinear boundary of a cargo hatch, the immutable laws of physics assert their dominance with merciless efficacy. An imperceptible fissure begins to form. Within a pliable, ductile alloy, such a rupture would typically cease, its progression absorbed by the material's inherent capacity to deform and yield. However, in rigid steel subjected to significant tension, this nascent crack rapidly transforms into a swiftly accelerating fracture. The considerable energy sequestered within these inherent stresses acts as a potent accelerant, fueling the crack's relentless advance. Acute corners serve as critical focal points of strain, intensifying local stresses by factors of 3 or even more. The fissure gains momentum, occasionally surpassing the speed of sound through the steel, tearing through the vessel's hull before internal bulkheads or structural frames can effectively impede its devastating trajectory. The catastrophic rupture of the SS Schenectady, viewed in retrospect, made perfect analytical sense. Her construction had occurred during the depths of early winter, with welding sequences that inadvertently amplified internal stresses to their maximum potential. Consequently, her entire hull bore the burden of tens of millions of pounds of trapped, inherent tension. When the Portland morning temperature plummeted to a frigid 28 degrees Fahrenheit, the steel's inherent properties shifted, rendering it markedly brittle. The intense stress concentration at a particular hatch corner initiated the fateful crack. This fissure then discovered an unobstructed pathway through the continuously fused deck plates. Crucially, there were no riveted seams to slow its progress, nor any deliberate stress relief brakes designed to halt its relentless march. The ensuing fracture ravaged the ship in a matter of seconds, discharging decades' worth of accumulated energy in a singular, ruinous disintegration. Traditional vessels, constructed using rivets, were notably immune to this specific type of failure, and understanding this distinction profoundly elucidated why welding techniques had, for a time, appeared to carry a peculiar curse. Riveted construction is, by its very nature, fundamentally segmented. Each individual riveted plate functions as a distinct, separate element within the overall structure. Cracks that might initiate within one panel invariably encounter a riveted seam and are effectively arrested there. The overlapping plates and the numerous mechanical fasteners collectively create inherent, natural barriers to crack propagation. In stark contrast, welded ships are seamless, continuous structures. A crack originating in a single plate can thus traverse unimpeded through hundreds of feet of uninterrupted welded seams. The very efficiency that enabled welded ships to be constructed with remarkable celerity also rendered them acutely vulnerable to catastrophic failures that riveted vessels simply could not experience. The Liberty ship's characteristic squared-off design further exacerbated this inherent problem. British maritime architects had specifically mandated these rigid, angular corners primarily for the practical advantage of facilitating easier and faster cargo loading and unloading. However, what was tragically overlooked was the critical fact that sharp internal junctures create severe stress concentrations, which can amplify applied loads by enormous, unforeseen factors. Consequently, every single wave that caused the hull to flex sent intense surges of stress spiking directly through these vulnerable corners. When combined with the pre-existing residual welding stress and the steel's increased brittleness at low temperatures, these corners transformed into critical sites for crack initiation, merely awaiting the precise confluence of environmental conditions to precipitate a devastating, catastrophic failure. Henry Kaiser, a titan of industry, fully grasped the profound implications of these unsettling test results for both his expansive industrial empire and the overarching national war effort. In January 1944, he faced a pivotal moment and made a momentous decision that would either unequivocally validate his revolutionary industrial methods or irrevocably expose him as a reckless profiteer who had callously dispatched thousands of American sailors to sea in fundamentally flawed vessels. He issued an immediate and complete cessation of all Liberty ship production at Richmond Yard 2, simultaneously diverting all available resources to the development and construction of an entirely new class of vessel, the Victory ship. This was far from a mere cosmetic adjustment or a minor modification. It represented a radical, foundational redesign, meticulously engineered around Bessie Hamill's groundbreaking observations regarding welding techniques and the dearly bought, painful lessons irrevocably inscribed in the fractured hulls of ships across two vast oceans. The sheer audacity of this gamble was truly immense. Liberty ships were, at that critical juncture, still desperately required to sustain the Allied war machine. German U-boats had, since 1939, tragically sent over 2,000 Allied merchant vessels to the frigid depths of the ocean. The impending invasion of Europe, still several months away in early 1944, was poised to demand the most extensive amphibious logistics operation in the entire annals of human history. In this dire context, every single ship held vital, strategic importance. Yet, Kaiser was wagering his entire reputation and fortune on the audacious belief that he could successfully implement Hamill's innovative sequence welding system, fundamentally redesign the hull to entirely eliminate perilous stress concentrations, significantly improve the steel's metallurgical specifications, and somehow manage to maintain production speeds that were already widely considered nothing short of miraculous. His numerous industrial competitors were convinced he had completely lost his sanity. Meanwhile, congressional investigators sharpened their proverbial knives, poised to condemn him severely should his ambitious production overhaul falter and collapse. Kaiser's dedicated engineers embarked on a systematic process, meticulously working backward from every identified point of structural failure. Consequently, every single rectilinear corner present in the original Liberty design was meticulously replaced with smoothly rounded transitions. The critical hatch openings, which had tragically served as the genesis for so many previous cracks, were comprehensively re-engineered with generously proportioned radii, thereby effectively nullifying the stress multipliers that had previously transformed routine operational loads into potent fracture initiators. The thicknesses of the deck and hull plates were painstakingly recalculated, not with the primary objective of merely adding superfluous strength, but rather to meticulously ensure that stress distribution precisely corresponded with the newly implemented, advanced welding sequences. Furthermore, structural frames were strategically repositioned to inherently align with natural stress relief points, rather than inadvertently creating antagonistic forces against the intended welding pattern. The very composition of the steel itself underwent a significant transformation. Kaiser's astute metallurgists specified a novel alloy designation, specifically formulated to possess demonstrably improved toughness at low temperatures. The carbon content within this new alloy was marginally reduced, while the manganese content was correspondingly increased. Small, yet crucial, additions of nickel, a metal that was both expensive and strictly rationed for the production of armor plate, were rigorously justified by compelling evidence demonstrating that a mere 0.25% nickel content dramatically enhanced the steel's inherent resistance to brittle fracture. The Maritime Commission initially hesitated at the increased expense until Kaiser persuasively presented detailed calculations, unequivocally proving that the prevention of just one single ship loss would more than offset the entire cost of the upgraded steel for an astounding 50 vessels. Consequently, in March 1944, the revised, superior steel specification received official approval. Following these material and design innovations came the truly monumental undertaking of comprehensively retraining the vast workforce. By early 1944, the Richmond shipyards alone employed an astonishing number of over 90,000 workers. Thousands among them were welders, who had acquired their trade through accelerated, week-long crash courses, mastering only just enough rudimentary technique to lay straight weld beads at the breakneck speeds required for wartime production. Now, these same individuals were suddenly tasked with understanding complex concepts such as welding sequencing, effective stress relief procedures, and sophisticated thermal management. In response, Kaiser established specialized welding schools directly within the shipyard facilities, strategically reassigning highly experienced welders, such as the insightful Bessie Hamill, from the production line to serve as instructors. Crucially, every single welder was issued a precisely numbered sequence card for each hull section, dictating, for example, "Weld number 1 here, number 2 there," ensuring unwavering adherence to the meticulously prescribed order of operations. The prefabrication system underwent a dramatic and extensive expansion. Rather than attempting to weld large, unwieldy sections directly on the shipways, where maintaining precise sequencing proved exceedingly challenging, Kaiser's meticulous planners opted to divide Victory's ships into numerous smaller, more manageable modules. These modules were then constructed in dedicated, specialized workshops. For instance, a single bow section might comprise as many as 50 distinct prefabricated assemblies, each meticulously welded under rigorously controlled conditions utilizing optimal sequences. Following this, these assemblies were systematically stress-relieved in specialized heating ovens before their final integration. This innovative modular approach empowered welders to commence their work from the geometric center of each small section and meticulously work outward, precisely emulating the groundbreaking methodology that Hamel had so effectively demonstrated, thereby eliminating the inherent constraints associated with assembling an entire hull simultaneously. The skeptics found ample justification for their doubts when the keel of the very first Victory ship was laid in February 1944. Its initial construction consumed 18 days, a pace notably slower than the existing records for Liberty ship production. Kaiser shipyards, it seemed, were no longer conjuring miracles. They were merely building vessels at what was, by comparison, an impressive but not astonishing speed. The second Victory ship, though marginally faster, still required 16 days to complete. Critics were quick to declare the entire program an unequivocal failure, citing it as irrefutable proof that achieving both quality and speed in wartime shipbuilding was fundamentally incompatible. Kaiser, however, steadfastly ignored their pronouncements. His focus was not on near-construction timelines, but rather on the meticulous crack inspection reports. The crucial revelation was that the first two Victory ships, upon thorough post-construction inspection, exhibited absolutely zero stress cracks. Not merely a reduction in cracks, but an absolute absence. By April 1944, Richmond Yard 2 had undergone a profound metamorphosis, transforming into a meticulously choreographed ballet of steel, intense heat, and precise human collaboration, an operational marvel that would have been deemed utterly impossible just 2 short years prior. The facility no longer bore the appearance of a conventional, traditional shipyard. Instead, it resembled an enormous, sprawling assembly plant, characterized by distinct, specialized fabrication zones that continuously fed a central assembly area where ship hulls materialized with astonishing rapidity. Kaiser had ingeniously adapted Henry Ford's revolutionary moving assembly line concept, but with a crucial modification. Instead of the product itself moving through stations, specialized teams of workers systematically rotated through stationary construction stations at precisely timed intervals. The intricate process commenced within the expansive prefabrication sheds, which were massive, covered structures where skilled welders meticulously worked on hull sections, none exceeding 30 feet in any dimension. Each individual section was accompanied by its own specific sequence card, serving as a precise operational guide. For example, a single bottom plate assembly might necessitate 47 distinct individual welds, each meticulously numbered and color-coded for clarity. Welders invariably began at position 1, which was always the geometric center of the section, and methodically worked their way outward in either a spiral or radial pattern. Supervisors diligently patrolled the shop floor, armed with comprehensive checklists, ensuring strict adherence to the prescribed order and preventing anyone from skipping ahead. After every set of 10 welds, the completed section was carefully transported into a specialized stress relief oven, where it was heated to an intense 2,100 degrees Fahrenheit and then allowed to cool slowly and gradually. This meticulous annealing process allowed the steel's internal crystalline structure to relax, effectively dissipating residual stresses before they could accumulate to potentially hazardous levels. The raw steel itself arrived at the yard already pre-cut and pre-formed from specialized rolling mills that had been completely retooled specifically for Victory ship production. Unlike the earlier Liberty ships, where yard workers were required to cut and shape individual plates on site, Victory ship components arrived meticulously prepared and ready for immediate assembly. Curb bow sections, for instance, came preformed to exact and stringent specifications. Deck plates featured pre-drilled bolt holes, designed for temporary alignment during assembly. Frame sections were delivered as complete, pre-welded assemblies. This extensive preparation work, executed in highly controlled factory environments, effectively eliminated numerous variables and guaranteed an unparalleled level of consistency across thousands of individual components. The final assembly process on the building ways followed a radically different and innovative sequence compared to Liberty ship construction. Instead of the traditional method of commencing at the keel and progressively building upward, Victory ships were assembled by bringing together large, pre-constructed modules almost simultaneously. The engine room section, the various cargo hold sections, and both the bow and stern components were all fabricated in parallel. These massive units were then precisely lifted by colossal gantry cranes and positioned into place in a single, intricately coordinated operation. On May 12, 1944, Yard 2 achieved its most ambitious assembly feat to date. 17 major modules, collectively representing an astounding 85% of a complete hull, were accurately positioned and flawlessly aligned in a mere 11 hours. And subsequently aligned within a remarkably brief period of just 11 hours. Following this precise preparation, the team of expert welders then meticulously joined these prefabricated modules. They employed the identical center outward welding sequences previously established, but critically, they were now integrating sections that had already undergone stress relief, rather than embarking on the inherently more challenging task of constructing stressed components from their nascent stages. The ambitious 5-day construction target was realized through an unyielding pursuit of efficiency, scrutinizing and optimizing every single minute of the shipbuilding process. To facilitate seamless operations, dedicated night shifts were responsible for strategically positioning all necessary materials and components, ensuring they were readily available for the day shifts to commence work without delay. Specialized quality assurance teams performed the singular, vital function of verifying alignment and weld integrity, proactively detecting any potential imperfections before they could escalate and compromise the structural soundness of the vessel. Mobile cranes meticulously followed predetermined, synchronized routes, delivering essential components to the various welding stations with astonishing precision, often within precise 5-minute logistical windows. To combat the pervasive issue of fatigue-induced errors that frequently marred prolonged welding sessions, welders operated in a rigorous rotation system, 30 minutes actively engaged with the torch, followed by a mandatory 10-minute rest period, thereby upholding a consistently high standard of quality. Kaiser ingeniously implemented a management strategy he termed the critical path method, a sophisticated system designed to meticulously track which construction tasks constituted potential bottlenecks, and which could be executed simultaneously. Should the installation of structural frames be progressing ahead of schedule while pipe fitting operations lagged, for instance, he would immediately reallocate personnel, deftly maintaining an optimal equilibrium across all concurrent construction phases. Every instance of delay, every minute deviation from the established schedule, was rigorously documented and subjected to thorough analytical review. Daily morning meetings served as crucial forums where the previous day's performance was critically evaluated, with teams collaboratively identifying and implementing solutions to minor issues before they could burgeon into catastrophic delays. The pinnacle of this optimized process occurred on June 27, 1944. On this historic date, the SS Benjamin Warner, designated Victory Ship Hull No. 23, achieved completion from the initial laying of her keel to her comprehensive sea trials in an astonishing 5 days and 11 hours. This achievement was far from a mere stripped-down demonstration vessel. Rather, the SS Benjamin Warner stood as a fully equipped, combat-ready cargo ship. She boasted robust defensive armaments, comprehensive electrical systems, a meticulously functioning engine room, and every single connection point, or more accurately, every weld, was executed in strict adherence to the newly implemented stress relief protocols. Crucially, her hull presented no evidence of cracks whatsoever. A meticulous post-construction inspection meticulously confirmed that her internal stress levels remained well within normal operating parameters. When the Warner embarked upon her inaugural shakedown cruise, she performed with impeccable reliability, navigating challenging conditions that would have undoubtedly caused structural failure in the earlier generations of Liberty ships. The 5-day Victory ship represented considerably more than just an impressive feat of accelerated construction. It heralded a profound and comprehensive reimagining of how intricate mechanical systems could be efficiently manufactured, particularly when advanced engineering principles were harmonized with the practical realities of large-scale construction. Bessie Hamill's initial keen observation had precipitated a cascading effect, culminating in a systematic and sweeping transformation of the industrial shipbuilding sector. The Victory ships that emerged from Kaiser's thoroughly redesigned production system were, at their very core, fundamentally distinct vessels from their Liberty ship predecessors. Even though a casual observer might perceive them as similar cargo carriers with identical operational mandates, the intrinsic differences commenced at a microscopic, molecular level and permeated every subsequent aspect of their design and construction. Where the Liberty ships had been conceived as emergency stopgaps, hastily assembled to meet an urgent wartime need, the Victory ships were meticulously engineered solutions, specifically designed to address and mitigate every failure mode that had tragically manifested, often written in the ultimate sacrifice of sailors who had braved treacherous seas aboard fracturing hulls in the frigid Atlantic. The enhanced steel specification proved to be an absolutely pivotal development. This innovative alloy, officially designated as killed steel, due to the strategic addition of aluminum during its production process to meticulously eliminate oxygen, exhibited dramatically superior toughness, particularly in low-temperature environments. Rigorous laboratory analyses conclusively demonstrated that the critical transition temperature, the precise point at which steel undergoes a detrimental shift from ductile, flexible behavior to brittle, fracture-prone characteristics, had plummeted from approximately 40 degrees Fahrenheit in the steel utilized for Liberty ships to an impressive near 5 degrees. This substantial 35-degree improvement meant that Victory ships were able to retain their essential structural flexibility even in environmental conditions that would have rendered Liberty hulls into dangerously fragile and susceptible shells. While this advanced material commanded a cost premium of 8% per ton, the resultant gain in operational performance and safety was, quite simply, incalculable. Each minute structural detail of the Victory ship meticulously reflected the newly acquired, profound understanding of stress concentration and the dynamics of crack propagation. The adoption of gracefully rounded hatch corners, which might initially appear to be a minor aesthetic modification, actually served to reduce localized stress concentrations by a remarkable margin exceeding 60%. Detailed engineering calculations unequivocally demonstrated that the sharp, unyielding 90 degrees corners present in the Liberty ships generated stress multipliers ranging from 3.5 to 4 times the nominal hull stress. In stark contrast, the Victory ships, thoughtfully engineered, generous radius effectively maintained stress multipliers below a critical threshold of 1.8. In practical operational terms, this meant that a powerful wave impact that would inevitably initiate a dangerous crack in a Liberty ship would, in a Victory ship, merely induce a controlled flex within the hull, well within its normal, safe elastic limits. The hull plates themselves were ingeniously installed, incorporating sophisticated crack arrestor features directly into the fundamental structure. Rather than relying solely on continuous welds that stretched for hundreds of feet, Victory ships strategically integrated riveted seams at carefully determined intervals. These hybrid connection points were not accidental. They provided intentional discontinuities within the structure, serving as critical barriers where a propagating crack, upon encountering a mechanical joint, would effectively lose its destructive energy, thereby potentially halting its advance before it could consume the entire hull. This groundbreaking design philosophy explicitly acknowledged the possibility that cracks might indeed initiate, but crucially, it engineered multiple robust arrest mechanisms to actively prevent their catastrophic propagation. It represented a paradigm shift towards defensive engineering, meticulously planning for potential failure modes rather than operating under the precarious assumption of inherent structural perfection. At critical stress points throughout the vessel, structural frames were purposefully doubled, meticulously creating redundant load paths. This innovative approach meant that if a single frame were to develop cracks or suffer damage, adjacent frames could effectively assume and carry the distributed load, ensuring the ship's continued integrity until necessary repairs could be safely conducted in port. Liberty ships, in stark contrast, possessed no such inherent redundancy. A singular frame failure in these earlier vessels often precipitated a progressive, cascading collapse as structural loads were catastrophically redistributed to already overstressed adjacent structures. Consequently, Victory ships possessed the remarkable capability to sustain damage that would undoubtedly sink a Liberty ship, yet still remain fully operational, perhaps limping to port uncompromised but fundamentally functional structural elements. The sophisticated welding sequences, meticulously developed from Bessie Hamill's critical observations, were rigorously codified into extremely detailed procedures that governed every single joint throughout the entire ship. The comprehensive procedure manual spanned hundreds of pages, specifying not only the precise sequence of welds, but also the critical thermal management protocols to be observed between successive passes. Welders received extensive training to diligently monitor the interpass temperature, the precise heat level of the base metal in the interval between consecutive weld passes. If the steel's temperature ever exceeded a critical threshold of 400 degrees, all work was immediately halted, and operations would not resume until the material had naturally cooled. This stringent control effectively prevented the cumulative heat buildup that had been a primary cause of massive distortion in Liberty ship construction, where welders sometimes worked continuously on lengthy seams, superheating the steel into warped, highly stress-riddled configurations. Quality control ascended to an almost obsessive level of scrutiny. Every completed weld underwent meticulous magnetic particle inspection, a sophisticated technique where finely dispersed iron powder, under the influence of magnetic fields, revealed microscopic cracks that were utterly invisible to the naked eye. Further, ultrasonic testing was employed to thoroughly check internal weld quality, guaranteeing full penetration and the complete absence of hidden voids or imperfections. X-ray inspection provided an even deeper level of analysis for critical structural welds, generating permanent photographic records that meticulously documented the integrity of each weld. Crucially, no ship was permitted to be launched until inspectors had unequivocally certified that every single weld met the exacting specifications. Initially, the rejection rate for welds was notably high, with nearly 15% of welds failing inspection in the very first Victory ships. However, through intensive training and experience, the welders rapidly assimilated the new procedures. By mid-1944, the rejection rates had plummeted to below 3%, a powerful testament to the efficacy of the rigorous training programs and the exceptional clarity of the newly implemented welding procedures. The ultimate validation of these innovations emerged unequivocally in active operational service. Between June 1944 and the cessation of hostilities in August 1945, a formidable fleet of 531 Victory ships entered service. A truly remarkable statistic confirms that not a single one of these vessels suffered a catastrophic hull failure. A minor incidence of cracks did appear in a mere handful of ships, typically localized stress concentrations that vigilant inspection teams detected and addressed before they could propagate into larger issues. These minor cracks were promptly repaired utilizing the identical stress relief welding procedures, and the ships were swiftly returned to active duty. The stark contrast with the operational history of Liberty ships was absolute and damning. The profound human arithmetic of Victory ships versus Liberty ships vividly played out across two vast oceans during 1944 and 1945, indelibly written in the countless lives saved and critical missions successfully completed that would have otherwise culminated in disaster aboard earlier, less resilient vessels. A poignant example of this resilience occurred in April 1945 when the SS Wanda Fuka, a Victory ship, struck a naval mine off the coast of Okinawa. The violent explosion ripped a substantial 20-foot gash in her hull, positioned precariously below the waterline. The crew, acutely aware of the tragic fate of many Liberty ships, braced themselves for the expected catastrophic crack propagation that typically led to their demise. However, to their immense relief, the fracture miraculously halted at the very first riveted crack arrestor seam. Remarkably, the Wanda Fuka was able to make port under her own propulsion, underwent repairs in an astonishing 6 days, and was swiftly returned to active service. In a chilling parallel, the Liberty ship SS Richard Hovey suffered a comparable mine strike in February 1945. This vessel, however, cracked longitudinally for a devastating distance exceeding 90 feet, ultimately broke her keel, and tragically sank within a mere 14 minutes, resulting in the heartbreaking loss of 37 crew members. The intricate logistics of the Pacific campaign would have been utterly unattainable without the unparalleled reliability afforded by the Victory ships. By June 1944, American forces were relentlessly advancing across the Central Pacific, pushing steadily towards the Philippines and ultimately the Japanese home islands. Each successive island advance demanded the transportation of millions of tons of vital supplies across thousands of miles of vast ocean. While Liberty ships were capable of undertaking these arduous voyages, their inherent structural fragility necessitated reduced cargo loads in tempestuous seas, slower transit speeds to meticulously minimize hull stress, and the ever-present, terrifying risk of catastrophic structural failure in remote locations far from any possibility of rescue. In stark contrast, Victory ships routinely operated with full cargo loads at their design speed of 15 knots, a significant 3 knots faster than Liberty ships, navigating through notoriously typhoon-prone waters without the paralyzing fear that a frigid night and turbulent seas might cause their hulls to fatally split apart. The compelling numerical data unequivocally underscored this narrative of superior performance. Between D-Day in June 1944 and VJ Day in August 1945, Victory ships collectively transported an astounding total of over 18 million tons of critical cargo, with absolutely zero losses attributed to structural failure. They frequently operated in the perilous North Atlantic convoys, where seawater temperatures routinely plunged below a frigid 35 degrees, conditions that had previously fractured dozens of Liberty ships. Furthermore, they bravely traversed the treacherous Arctic routes to Murmansk, delivering vital Lend-Lease supplies to the Soviet Union, a theater where near-freezing seawater temperatures had rendered Liberty ships terrifyingly vulnerable. The SS Hobart Baker, a resilient Victory ship, successfully completed an impressive 17 Murmansk runs without developing a single stress crack. In stark contrast, the Liberty ship John Walker, attempting to navigate the very same demanding route, developed critical cracks on only her second voyage and was subsequently withdrawn from Arctic service permanently. Crew morale experienced a profound transformation when mariners transitioned from the notoriously problematic Liberty ships to the more robust Victory vessels. Personal narratives collected in the aftermath of the war vividly illustrate the immense psychological strain endured by those serving on ships widely known for their propensity to spontaneously fracture. Merchant sailors frequently reported pervasive anxiety, particularly exacerbated by frigid weather conditions. Restful sleep became an elusive luxury, as every creak and groan emanating from the hull seemed to portend an imminent structural failure. Consequently, some sailors actively sought transfers or simply declined to embark on specific Liberty vessels with documented histories of cracking incidents. The introduction of Victory ships, however, instilled a renewed sense of confidence. Crews felt empowered to push these resilient vessels to their operational limits, fully aware that the ships could withstand such rigorous demands. This newfound assurance directly translated into enhanced mission effectiveness, significantly faster turnaround times in port, a greater willingness to navigate through adverse weather, and the ability to execute aggressive maneuvers when confronted by aerial assaults. The pivotal Battle of Leyte Gulf, which unfolded in October 1944, starkly showcased the Victory ship's remarkable combat resilience under environmental and confrontational circumstances that would have utterly devastated their Liberty ship counterparts. A substantial contingent of 16 Victory ships provided critical support to the invasion fleet, diligently transporting vital ammunition, aviation fuel, and various supplies amidst relentless kamikaze assaults and treacherous typhoon conditions. During this intense period, the SS Kyle Johnson sustained significant near-miss bomb damage, which resulted in buckled deck plates and discernible cracks across 3 frame sections. Despite this considerable damage, she steadfastly continued her operational duties, offloading essential cargo under hostile fire for a grueling 4-day period before finally withdrawing for necessary repairs. The intrinsic structural redundancy and ingeniously incorporated crack arrestor features of the Victory ships were instrumental in preventing what might have been minor damage from escalating into a catastrophic structural collapse. In stark contrast, Liberty ships suffering comparable damage typically had to be abandoned, as their cracks would rapidly propagate beyond any hope of control. The underlying economic rationale, though stark, presented a clear and undeniable truth. The construction cost for each Liberty ship amounted to approximately $2 million. Victory ships, on the other hand, commanded a price tag of $2.6 million, rendering them a notable 30% more expensive. However, statistical analysis based on actual failure rates through 1944 indicated that a Liberty ship carried a significant 4.6% probability of experiencing catastrophic structural failure during its operational lifespan. Such devastating incidents typically claimed the lives of an average of 18 crew members per occurrence and resulted in the complete destruction of cargo valued at 3 to 5 times the original construction cost of the vessel. The impressive zero failure rate demonstrated by Victory ships meant that their additional $600,000 construction cost was effectively recouped within the first 6 months of service, simply through the elimination of inherent risks and a corresponding reduction in insurance premiums. By the culmination of the war, merchant mariners had coined a somber yet insightful adage that succinctly encapsulated the fundamental differences between the two ship types. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those meticulously crafted inches, representing the painstaking attention to welding sequence, the rigorous and obsessive quality control measures, and the ingeniously engineered crack arresters, translated into decades of reliable service life, a stark contrast to the desperate prayers offered whenever a Liberty hull groaned ominously in frigid seas. Bessie Hamel quietly transitioned back to civilian life in 1946, her departure marked by neither public fanfare nor widespread recognition, save for a commendation letter from her shipyard supervisor. She never received a prestigious medal, nor was she ever called upon to testify before Congress, nor did her name ever appear in the technical papers that subsequently documented the revolutionary advancements in welding she had so profoundly influenced. The established engineering community readily assimilated her groundbreaking insights, subsequently rephrasing them in complex mathematical language and esoteric academic terminology, ultimately publishing them, as if these profound discoveries had originated from sterile laboratory research rather than from the practical, on-the-ground observations of a dedicated night shift welder. For many decades, standard welding textbooks meticulously detailed stress relief sequencing protocols without ever acknowledging the extraordinary woman who had first discerned its critical necessity while observing hull plates distorting beneath the intense heat of her welding torch. Nevertheless, her indelible legacy profoundly permeates modern engineering, extending its reach far beyond the confines of shipbuilding. Virtually every welded structure constructed today, encompassing everything from towering skyscrapers to extensive pipelines and robust pressure vessels, adheres to sequencing protocols that are directly descended from the pioneering procedures meticulously developed at Richmond Shipyard in 1944. The American Welding Society Structural Welding Code, initially promulgated in 1947, formally codified center outward welding sequences and stringent stress relief requirements as mandatory industry standards. The colossal undertaking of pipeline construction across Alaska in the 1970s heavily relied upon welding procedures that explicitly referenced and incorporated methods perfected during Victory ship construction to effectively prevent cold weather cracking in the challenging Arctic conditions. The Trans-Alaska Pipeline, an engineering marvel spanning 800 miles of welded steel, safely transports hot oil through persistently sub-zero temperatures, a testament to the profound understanding engineers gleaned from the invaluable lessons imparted by Hamel. Modern bridge construction has similarly inherited and integrated these fundamental principles. The calamitous collapse of the Point Pleasant Bridge in West Virginia in December 1967, an event that tragically claimed 46 lives, cited residual welding stress as a significant contributing factor. The ensuing investigation unequivocally revealed that welds executed without proper sequencing had inadvertently locked dangerous stress concentrations into critical structural members. Subsequent post-disaster code revisions stringently mandated the implementation of the sequencing and inspection protocols that Victory ships had so effectively pioneered. Every welded bridge constructed since that time incorporates these essential requirements. Even the ambitious seismic retrofit of the iconic Golden Gate Bridge in the 1990s, which involved the addition of thousands of tons of welded steel reinforcement, employed sophisticated computer-modeled welding sequences meticulously optimized to minimize residual stress. These represented highly advanced iterations of the principles Hamel had so brilliantly demonstrated with hand-welded test plates back in 1943. The offshore oil industry repeatedly encountered and learned this critical lesson through harsh experience. The devastating Alexander Kielland platform disaster in Norway in 1980, an incident where 123 workers perished when the platform capsized, was partially attributed to fatigue cracks propagating from improperly sequenced welds. The catastrophic Piper Alpha platform explosion in 1988, which tragically resulted in the deaths of 167 men, originated with a crack in a welded pipe connection that had accumulated significant residual stress. Each of these profound disasters compelled investigators to meticulously scrutinize welding procedures, and each subsequent investigation invariably rediscovered fundamental principles that Victory ship construction had unequivocally proven 4 decades earlier. Contemporary offshore standards now stringently mandate stress relief heat treatment for all critical welds, a direct and undeniable echo of the specialized ovens Kaiser had installed in Richmond's prefabrication shops. Nuclear pressure vessels, designed to safely contain reactor cores under extreme temperatures and immense pressures, represent the ultimate and most demanding application of stress relief welding. The massive steel shells that encase these nuclear reactions simply cannot tolerate the initiation of any crack whatsoever. Welding sequences for these vital reactor vessels are meticulously planned with unparalleled computational precision, simulating complex thermal effects, and predicting residual stresses long before the very first weld is ever struck. The entire vessel then undergoes a comprehensive post-weld heat treatment in colossal ovens, precisely mirroring the process applied to Victory ship sections, thereby effectively eliminating any residual stresses that could potentially serve as failure initiation points. The pioneering engineers who designed these critical procedures in the 1950s explicitly and extensively studied Victory ship construction as their foundational and indispensable reference. Hamill's astute observation fundamentally reshaped the way engineers conceptualize fabrication processes. Prior to the advent of Victory ships, design and construction were largely disparate domains. Engineers meticulously designed structures, while fabricators were tasked with building them, and these two groups rarely engaged in substantive communication regarding how specific construction methods might impact overall structural performance. Victory ships conclusively demonstrated that the fabrication sequence was as critically important as the selection of materials or the structural design itself. Modern engineering education now comprehensively integrates manufacturing processes as essential components within design courses. Engineering students are now rigorously taught that even a theoretically perfect design, if executed with a flawed fabrication sequence, will inevitably yield inferior results when compared to a more modest design constructed using proper and proven procedures. The impressive 5-day construction timeline, while certainly noteworthy, was never the true measure of achievement. Kaiser's shipyards possessed the capability to sustain the rapid production speeds of Liberty ships indefinitely, continuously launching defective vessels that merely appeared seaworthy until their inevitable fracture. The actual miracle lay in the courage to deliberately slow down sufficiently to perform the work correctly, the profound willingness to halt production and fundamentally redesign processes based on the invaluable insight of a frontline welder, an insight that directly challenged long-established practices. That profound willingness to actively listen to frontline workers, to humbly admit that prevailing engineering theory had overlooked something critically important, and to courageously redesign entire systems based on observed reality rather than rigidly defended assumptions. That, indeed, was the true revolution. Every modern manufacturing methodology, from the rigorous Six Sigma to the efficient lean production to the comprehensive total quality management, inherently embeds this fundamental principle. The worker who directly observes the process often possesses a unique perspective that the engineer, calculating from a distant desk, simply cannot perceive. Bessie Hamill passed away in 1987 in Sacramento, her obituary merely noting that she had worked in wartime shipyards. Yet, every welded structure standing today, every pipeline traversing frozen terrain, every pressure vessel safely containing dangerous forces, every bridge gracefully spanning rivers, all of them carry her enduring legacy within their meticulously sequenced welds and precisely stress relief joints. This stands as a silent yet powerful testimony to the extraordinary welder who dared to question why ships were breaking and steadfastly refused to accept the complacent explanation of, "That's how it's done."